All right, and hello and welcome to Algorithms Live. So in this week, I'll be going over this problem, desert wind. This is a Topcoder problem from, the round is very old. It's 164, round 164. So it's a very old problem. I think it's kind of interesting, just a little bit weird. And I apologize to anyone. I messed up the time. I said in the blog that I'd be starting an hour before the Codeforce's educational round. And so the time announcement was correct, but I messed up the time announcement for the YouTube channel. So people might be an hour off from trying to view this live, but it seems we have a good number of people watching. So it seems like everything should be fine there. It should be a little bit shorter episode. I'm just going to focus on one problem this week, and it's just this desert wind problem, which I think is a little interesting. I'm helping with the SI UCF camp, which is a programming contest camp for high schoolers this year. So focusing mostly on that, but I carved out a little bit of time to discuss this problem with you guys, keeping the streak going for weeks. Okay, so let's dive right in and talk about why I think this problem is interesting. And I'm going to go to this grid view. I think it'd be interesting to see. And just talk about how this. So will it take less than an hour? I hope so. I definitely think I'm going to finish discussing this problem before the Codeforces round starts. I'm going to try live coding it. I don't know if I'll be able to code it correctly in an hour, but we'll see. Yeah, so it's going to be should be a shorter episode on the explanation side. All right, so let's just talk about this problem. So what we have here is we have a starting location. It's given as the @ symbol. Some x's, a dash is just going to be an empty cell. And what you're given is oases. I don't know what the plural of oasis is, but maybe it's oasis. But you're given a few of these, and you want to go through the desert and get to one of these oases. Your movement kind of looks like this. You can just hit all 8 cells. That's really where you can go. You can just go to any of these 8 adjacent cells. And you want to get to one of these oases with the minimum cost total. So the thing that makes this problem, so it looks like a standard shortest path problem. You can move in any of these directions, but it has a small twist that I think is interesting. After you choose which direction to go, so say you're choosing to go in, I guess before your choice, the desert decides to blow wind in some direction. So it can blow it in a diagonal direction, it can blow it in any of the 8 directions. And if it's whatever direction you chose, it'll take 3 days to get to the place that you want to go. But if you go in any direction that isn't directly against the wind, so let's say I go in this direction walking, then it only takes 1 day to get to the next location on the grid. So you get this really interesting problem here. So let's say what you want to do is the wind is actually your adversary and will always blow in the most inconvenient direction. I think that's what's interesting. So for this example, if the wind decides to blow in this direction, what you could do is if you go here, it'll take 3 days. But if you go here, it'll take only 1 day to move to the right. Oppositely, the wind could blow in this direction. And in that case, it would take 3 days to get here, but 1 day to get here, or 1 day to get here. So it'll always try to pick something that's annoying to you. And so this is actually the first sample. You're always able to do this in just 2 days going forward, as far as what you can start at one of these cells and reach one of these cells in 2 days. Yeah, so the way this works is on the first day, if it blows this way or this way, you end up in one of these cells in cost 1. So you're either in this in one cell or this in one cell, regardless of what choice you make for the wind. So if the wind decides to blow this way, you'll go to this cell. If the wind decides to blow this way, you'll go to this cell. And then you can hit from either of those positions, you can hit the oases. So a slightly inconvenient problem. I think the thing that makes this problem hard to think about just initially is you look at this, you don't really know which way you're going to go, and you don't really know which way the wind is going to go. Like what's the best decision for the wind versus what's the best decision for you, and it's kind of got this game theory element to it, even though it's some kind of shortest path problem. It also reeks of like a Dijkstra's type problem, but the choice I don't think is as obvious. So the first thing you want to do when you're attacking this problem is eventually you just start thinking, okay, what if I work backwards? So I know that if I'm at, let's say I'm at some oasis, the cost of being at that oasis is just cost 0. Like I know it doesn't take any more moves to get to that oasis. And now what I can do is I can just look at my adjacent cells, and I could update for each of these adjacent cells, what's the minimum cost to get to those adjacent cells. Basically, if I already know this cost, I could update that particular cost. The problem is, let's say I went here at this particular cell. Well, the wind obviously will try to blow against me. So this cost might be 3. So the next thing you realize is for every single cell that you're trying to update, you have 8 possible directions that it could go. If you already know what's the minimum cost to reach that oasis from each of these adjacent cells, well, the wind is going to blow in the direction of the one that's the shortest path. So let's say that this can reach the goal in cost 2, and then there's something else that can reach the goal in cost 3. Well, it might blow in this direction for cost 2, like if you just happen to know the optimal cost. So you would most likely take the second best wind direction. And that's the idea, is instead of doing your usual shortest path distance array, we're actually going to store what's the cheapest cost and what's the second cheapest cost for every single cell. And we'll continuously update them. So I guess this next problem is it's not really obvious what's the best order for costs. Usually if you're running a Dijkstra's, you always just, and so you can think of this as like a Dijkstra's problem from the oases. If you're running a Dijkstra's backwards, you usually know what's the next cell that you can process. It's the cheapest one that you've seen so far. But with these 2 cost functions like this, that it really doesn't play out that way. So the trick here is, even though we don't have negative cycles, the best algorithm to run here is Bellman-Ford. And so I'll just briefly go over what Bellman-Ford does and how it helps us. So Bellman-Ford is just the dumbest algorithm you can think of for running shortest path. So let's say I'm just going to make a regular graph and just briefly talk about Bellman-Ford. Okay, so everything else here is cost infinity to get to. And so the idea is you just loop over all the edges and update anything they're adjacent to with the shorter cost until nothing gets updated anymore. So I'd even try updating this edge. The costs don't improve. So the only ones that really improve are from the start node. So this goes down to cost 5. This goes down to cost 4. I loop through all the edges again. This goes down to cost 10 off of this node, or cost 9 off of this node, plus this edge. Just keep on relaxing. This one goes down to cost 6, but it actually improves this one to cost 5. Loop through all the edges again. This becomes cost 5, and that ends up being the best cost. And if I try updating again, you'll notice this graph doesn't improve anymore, so then I quit. So it's like, wow, improvements. Update each node through each edge. So really, if you're at some state I, so I'm trying to improve J, ends up being the min of state J and state I plus the edge that you're currently considering, the edge between I and J. And so if this ends up changing state J, then you've got to change, and you know to keep looping around. So it's a E times V algorithm because this is O of E, that piece in here, and this will run at most V times because the longest path in the graph is at most V in length. So it's a pretty simple algorithm. It works great for negative cycles. It'll loop forever if there are not negative cycles, but negative edge weights. So it's how you get around negative edge weights, but also works for dynamic programming problems or shortest path problems where you don't really know what the next choice state is going to be, which is exactly what we have here with this desert wind problem. So usually people tell you, oh, if you've got negative edges, that's when you start considering Bellman-Ford. But I like this problem because there's no negative edges, yet Bellman-Ford is really useful. So just running through the Oasis example, I'm going to just take a bigger example, draw it out, and I'll just show you how Bellman-Ford helps us in attacking the problem. So I'll put in these, draw a more complicated case. And I start here, so I'll just put this as cost 0. Well, this is the start state. And these are the wind locations. The asterisks are the oases. So what I'll do is I'll just replace these with zeros. And that's cost 0, and I'll replace this with 0. Okay, so what happens is if I'm running my Bellman-Ford, I just loop over all the cells. And when I get to some cell here, I have two costs that I want to care about. If I update this one is going to say, well, I could get here at cost 3. My two cheapest movements are something that is 1 away and something that's infinite away right here. So those are my two cheapest movements. And what happens is I just change this after I figure out my two cheapest movements. I change a cheaper movement to be cost 3, so this updates to 3. And so then I go over here, loop over all the cells. This one has the exact same thing. It's 3 and 3 and infinity, basically, are my two cheapest costs. I go into this cell. My two cheapest costs are 0 and 1. Well, it's already cheaper. Like this is already cost 0, so I guess I don't update that. But this one, the cheapest cost is looping through in row major order. I guess I'd update this one first. This one is also 3 and infinity, so it comes out to cost 3. This one's interesting. So I end up having two costs, cost 1 and cost 1. So my cheaper cost is 3, but I actually save in my state cost 1, right? Because I could move to this cell or I could move to this cell, and it ends up being cost 1. So I look at the 8 adjacent cells, and I can get this one down to cost 1 if I end up moving there. So then I loop through again. I end up hitting this cell. It's cost 3, cost infinity, so this comes out to 6. Go to this cell, and I've got a few choices here. I have something cost 0 and cost 1. So the cost 0, 1 comes out to 3. But the cost 1 cell that I can reach. Actually, it takes 2. So it's cost 1 and cost 2 to move for this. So I can move here with cost 2. I can move here with cost 1. So I get 1, 2. But then I up it by 2 because it's 2 greater. So this comes out to 3 as well. So I'm just updating my costs, just relaxing, and I've looped through all the edges at this point. So all possible states, all possible moves. And it comes out to 3, 2. And so I just loop through it again because I still have changes. So I get here, there's nothing to update. I get out to here, so I can get to 3. So this doesn't improve from this location. This doesn't improve from this location. I get out to here. Well, I can reach this cell at cost 3. So I get another, I get something like 6 infinity. So this comes out to 6. Go out to here. Well, the 2 cheapest costs are 3 and 3. And so I just take the cheaper one. This comes out to cost 4. So then I look at this state. I get 1 and 0. So I get 1 and 2 are my 2 cheapest costs. This gets bumped up to 4. So it's better to take that 2. So actually improve this one to cost 2. Oh, and I guess I should have improved the at symbol, but I'll do that in the last pass. Go through here. This one has cost 3, cost 0, and cost 1. So it's 1 and 2 again. Move that up to cost 3. I guess this would have been a 3, 2 off of here. So this comes down to cost 2. And you can keep on relaxing here until there's no more changes. So if I do one more loop again, my 2 cheapest costs are 1 and 3, but I have to pay that cost. So it's 2 and then 3 off those 2. And I penalize the cheaper one, so it's 4 and 3. So this ends up being cost 3. So in terms of the movement, here's how this works. If the wind will try to penalize me from going to this really short path, so I'll have to come down here. And if it penalizes me from going directly to the oasis, I can take this one. Or if it doesn't penalize me there, I can just move here in 2 costs. So the answer for this problem, it seems to be 3 for that case. And if you look at the second sample on the Topcoder problem, it comes out to 3. So we did get a comment, 4 plus 1 plus 1 equals 6. Yeah, I might have messed up the way I'm doing the cost. So maybe I'm not explaining it entirely correctly. So let's just, I'll step back for a second. So imagine I'm at a state here, and imagine these are my costs around me. Maybe I change the state. So what I do is I take these cheapest costs, I look at the 2 cheapest costs, and I get 1 and 2, but I need to add 1 to them because if I walk normally, it ends up being 1. So my options are update my cost to cost 2 or update my current cost to cost 3. 2 cheapest costs because the wind is going to blow in the direction of the cheaper one to make my life hard. So this one actually goes up by 2 more because remember it takes 3 days instead of 1 day to move to the next one. So that goes up to 4. So if I'm an adversary, my adversary is always going to blow the wind in this direction on this particular sample. And so I'm going to update this particular position, go to this position because it's cheaper. There's also the case where maybe this was cost 3. So sometimes, actually, let's make this cost 8. Let's make this cost 4. It may be cheaper in a scenario like this to actually go against the wind because none of the other cells that I'm reaching make any sense. So in this case, I go against the wind because my costs will be cost 2, and then the next cheapest cost will be cost 5. Bumping this up by 2 makes 4, so that's the cheapest cost to create. And so I just update this position. And so the idea is to continuously use Bellman-Ford to do the updates. So I may not have worked out the sample entirely correctly by hand, But when I try coding this, what I'm going to do is I'll just print out the matrix after every single run of the Bellman-Ford. So I'll just put a print statement in here in my Bellman-Ford, and you can see the cost matrix changing in real time. And that's the idea. I'm just going to run a sample like that. I was having trouble getting on the Topcoder arena, but I've looked at some of the old Topcoder videos I've done in the past, and I think it's hard to see the code in the arena when I do them. So I'm actually going to code this one in VI and then paste it in the Topcoder arena. The arena applet wasn't working this morning when I was playing around with it, and I didn't have time to play with it. So I'm actually going to try the web interface for the first time. So we'll see how that goes. Okay. We did get another question from a viewer. Are Topcoder problems harder than code forces and CodeChef? I feel like Topcoder, since it has smaller bounds, you can't do really big bound problems just because of the limitations. So it's much easier when you're doing a Topcoder problem. It kind of forces you as a writer to write in a more ad hoc way. And so you get these really clever problems, maybe a little more mathier problems in Topcoder, where code forces and CodeChef, you tend to get really big bound problems, kind of more similar to the IOI or some ICPC type problems. So they're kind of like different flavors of problems, I'd say. And some people favor the Topcoder ones, some people favor the code forces, CodeChef ones. But I think it's just fun to compete in different types of contests. I like going back to some old Topcoder problems because you can find gems like this one. I think this problem's fairly unique idea. I've seen a few other problems that use Bellman-Ford in this way. There's an old Northwest European problem, I think. I'll have to go find that one again. Maybe I'll post it in the blog a little bit later. But it's got a similar idea to this desert wind one, where you're doing this relaxation because you're not sure what the next state should be. And I think that's what makes it cool. So yeah, I think Topcoder has really nice problems. I also, I feel the same way about AtCoder. You see that in the AtCoder episode, just sharing some of the problems Makoto has been working with and some of the writers on AtCoder. I've been impressed looking at those sets. Yeah, so it's less about problem difficulty for me, more about problem beauty, I'd say. Okay, so I'm just going to try coding this one, live coding this one. So if you're competing in the educational round, feel free to just leave and go compete in that when it gets to 11 a.m. Well, it's 11 a.m. here in Orlando, but yeah. Yeah, I also wanted to point out before I start coding, I thought this was neat. This is the episode 25 of Algorithms Live, and it's education around 25 on code forces. So it's just a nice coincidence. Okay, so let's start coding this desert wind one. And maybe I'll code everything in the oh, this is distance. We'll do width and height. Usually they say you want to do things in row major order for these kind of problems, and I've just gotten this really bad habit of doing everything like X and Y coordinates. And sometimes I switch back to the other way, but for something I can visualize, I like it this way. But then, of course, when I print out my answer, it's way more convenient row major. Okay, so we need an infinity value. So that'll work. And then I need to, yeah, I'm going to use a blocked array. If some of these cells are blocked, I think it's just a little more convenient to think of it this way. So I need to find where my goal is. All right, so if map that's blocked, so there. So I'm just pulling some standard bookkeeping stuff out at the moment. And then what I'll do is I'll make distance ij if it's an oasis. Maybe I'll refactor this. Mainly to prevent bugs, because if I type I or J here before I, like in just one of these if statements, then I just have this cascading bug, and I've made bugs like that before, so I'm coding a little bit defensively there. So that's just a tip, because if I don't want to have to look through all these if statements and make sure I didn't type I and J. I make that bug all the time and burns me in Topcoder rounds. So what I'm doing here is just filling my distance array with infinity. So if you saw when I was doing Bellman Ford, I'm setting all nodes to infinity, and I'm working backwards from the oases. There could be multiple oases. And I'm just setting the distance to 0. I'm also saving where I start. So when I'm done with my Bellman Ford, I can just print out the I and J when I can't update anymore. So this is going to be my Bellman Ford. And so some of you may have noticed my color scheme for this episode is actually the VI desert color scheme. I thought that was appropriate, so I switched over. Probably a small thing, doesn't really matter, but I enjoy it. Okay, so now I basically set up my graph. I'm using the graph implicitly, so I'm not actually storing the transitions on the matrix. I'm just going to loop through all adjacent cells to loop through all the nodes. So I'll just go through all my nodes. And then for every node, I just go through all adjacent edges. Don't have to handle block cell. We'll just write it this way. And then I just want to update off of adjacent edges. So I'll call it cheapest neighbor 1 for the nearest neighbor, cheapest neighbor 2 for the second nearest neighbor. And so usually I'd code a dxdy array, but if I'm just looping through all my the 8 nearest neighbors, I usually code it this way. And it's probably not the best way of coding it, but I don't know why I do this. I need my next I and next j. I just look for out of bounds here. That's all I'm doing. So nj is less than 0, or nj is greater than height. Continue. I should probably use good style. Probably name my variables a little better here, but oh well. So I'm just looping through everything that I can reach, and I'm just gonna basically see what the cost is of going to that neighbor. So cost equals dist of ni nj plus 1. So what I'm doing is I'm just calculating that, and then this is just like the cost of getting to the next nearest neighbor. And then for the cheapest neighbor, what I'm going to do is, here's what I do. I do, if cost is less than the cheapest neighbor, because I want this to be the cheapest cost and this is the second cheapest cost. And this is how I typically code this if statement. If it's less than the cheapest cost, then we just slide the cost down. Like so. Actually, I want this less than or equal to. So let's say what happens is I have this value is 3, this cost is 3, and nearest neighbor 2 is 4. Then I want this to turn into 3, 3 and not stay at 3, 4. So that's why I use less than or equal to. So for this piece right here, all I'm going to do is if the cost is less than cheapest neighbor 2, mate for. That's a funny typo. And that's just that cascading costs. And so that'll update my 2 costs. So I end up with the 2 cheapest costs. And then all I do is I do dist ij. Actually, what I should do is call this new cost. So I'll take math.min of cheapest neighbor 1 plus 2, because that's the penalty I pay for being the cheapest. The wind's going to blow in the direction that's cheapest. Cheapest neighbor 2. So this is going to be the cheapest cost of moving to the next location. And then if new cost less than dist ij, then I've managed to update something. So I'm going to set that to true. Like I managed to update one of my edges, and then I just save the new cost. And so just for debugging purposes, I'm going to loop through everything and print every single time. Yeah. Sometimes it's good to actually write some like block testing debug code before you realize you're failing samples, just as like a sanity check. I think it's a worthwhile thing to do. Okay, so I want dist ij, and maybe I take this and make it 10. Yeah, and so we'll get like really big values, but for like certain infinities, but that's okay. And I'll be able to comment that out later. And I guess I should save my answer. So the way this works is if the goal x, goal y is infinity, return -1, return dist. That's pretty good. I think that's all we have to do. So this should work. Not super crazy. Hopefully it'll let me write code. Yeah. Failed system test. What a surprise. Cannot compile blank code. Oh, look, it let me copy and paste it. Cool. Let's try the web applet. Did not compile. Oh yeah, I need some kind of else if here. So line 75 should be else if. Code compiled successfully. So let's go to the test panel. So there's this like nice little test panel and I can run tests. Everything is wrong. So let's uncheck all and just run test 1. Yikes. It's doing update, 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 update. It's not respecting my print lines. So that's annoying. Yeah, I think I like the applet much better, honestly. Okay, I want to take a quick look at the test case here. Yeah, it's getting, the very first line is getting 3 for the update off that. I think I want to print here before the Bellman Ford. Take a look at what my cost matrix looks like. So initially, that looks correct. Why is that 0 thing 0? So it seems I'm putting 0 for my oases. Oh. Yep, that'll do it. So I'm just going to put in, there's my bug, put infinity there, and then just get rid of this else. Silly bug. Update value 2, correct. Okay, so maybe I'll erase some of this code. I'm getting samples right. So yeah, I wish the output was a little cleaner to read. So we'll try to push this through system tests. I'll run tests again, make sure I don't have any debug. And I'm getting all the right answers here. So run system test, failed system test. Dang. See if I can find an obvious bug. This is going to be a little harder to debug. I want to see some of the comments, see if something came up in the chat. How do you type the infinity symbol? I just put OO, like two O's, and it kind of looks like infinity. So it's not a special character. One cool thing is, like, if you're in a language like Swift, you can actually get all the Unicode code points. So you could actually type the infinity symbol for Unicode, and it would work. But Java doesn't allow that for its variable naming, which is probably smart. Right. Okay, so there's some education around stuff going on too, discussion on the chat. Yeah, I think the best thing is if you look at Swift, you can actually name your variables emoji. So you should play around with Swift if you haven't. And there's some great stuff about emoji and variable names. Just really amusing. Okay, so if it's blocked, don't update it. Fine. So it seems like I'm storing the graph correctly. Like this part doesn't seem to have a bug, but just in case, I'll run through the code real quick by hand. I think this is an example of a problem that it's hard to come up with test cases because you have to by hand solve them. So usually when I'm in contests, I actually just trace my code through in my head and try to figure it out. And there's not like a simple brute force I can write for this one. I'm just going to have to like figure out the bug in my code, like implementation. But if any of you have an idea for a really good case that you think I'll just break on instantly, just let me know. So C is, that's the infinity for goal X, goal Y. And I get a 0 here because that's my oasis. I reread the, try the case where everything is the oasis. Yeah, that might be a good one to try. Let's test this a little bit better. So I'm going to add a case here. Custom test case. What do these cases look like in Topcoder? So I will, I'm assuming what you mean is just put oases everywhere. Maybe I'll put the @ symbol in the middle. Yeah, it comes out to 1, which is correct. We expect that to come out to 1. Maybe I can make a line case too. So I could do X and then dash 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 star. Is it supposed to be dashes? Oh, we need to know. Wait, yeah, we need to start. Okay. Map must contain between 2. Damn. You can fix that. Just make everything a wall. Yeah, 12. So 3, 3, 3, 3. Yeah, that seems to be correct. So I'm just going to trace through the code by hand real quick, see if I can find this bug. So this handles the normal, this handles a blocked node, this handles the @ symbol, this handles an oasis. Then we loop through Bellman Ford, loop through all the cells. That's blocked, I don't do anything. Yeah, the one thing to always look for me is like mistyping I's and J's. That's one way I get burned a lot. Ni and j. If the cost is less than the cheapest neighbor, then I want to slide the cost down, replace the cost with the cheapest neighbor. If the cost is less than the second cheapest neighbor, then I just drop it in. That's suspect. But I don't see why that would happen. So maybe for safety, I'll put that in. But this is a minimizing function and it shouldn't go over. And I don't seem to be overflowing either. That's another thing to test for, is if you're looking at this code, one thing that could happen is you could get integer overflow and then break everything. I've definitely been burned by that. But the costs are only 1, so it doesn't seem like I should overflow an int. It's my blocked array. And if you have a test case to try, just drop it in the chat. Okay. Yeah, is overflow possible? Well, I don't think overflow is possible here. Is it allowed to have no oasis? Let's try that. Although I think my code will handle that, but we'll see. I'll add something here with no oasis. And Topcoder will... Actually, let's just copy this case. This is a good case to have. And I can just change it to no oasis. Yeah, you can have no oasis, but that doesn't seem to cause a problem. I wonder if you can have multiple starting points, though. That would be interesting. And have no more than one starting point. Okay, good, because my code would definitely not work in that case. So there's no oasis to hit. Yeah, really not sure what's wrong. Okay. Yeah, if you want to pull up the constraints, you can just find this on the applet as well, or somewhere else. You're going to read the problem a little more carefully. It says 8 adjacent cells. One cell to the, we must start at our current location and make it to oasis. Oh, that's annoying. Yeah, I need to not go through block cells. So I don't know if that's going to cause a problem with how I coded it, but just do it here to make sure that's correct. That's a bug, potentially, depending on this is. So if I end up going to a block cell, I definitely don't want to use that piece. Oh, right. So here's one thing that could happen is I could be counting that towards my 2 cheapest neighbors. Yeah, if I'm using my block cell. But I'm not sure why that would cause a bug. Make sure I don't have another bug sitting around here. So I don't want to process me if I'm a block cell, don't want to process me. Yeah, let's go into the applet again. And one of the things, if we want to know if that's a problem, I think one of the best ways to do it is just take this code out and just make a test case. Like that. -1. See, it's still like, even though there's a block cell, I'm still not getting through. But it is a bug. I mean, it's certainly what I'll try if I run out of time. Second cheapest neighbor cost is the cheapest neighbor 2. Set replacement seems fine. I should reverse these. Yes, one thing to try. I could try like a narrow test case. Oops. Parameter is invalid. Okay, so that executed and I didn't get runtime error. Let's go ahead and submit this code. Oh, so I guess that was the bug. Another thing is I could have just not hit submit when I submitted my code. That would have been tragic. I think my last submit was much earlier than that. And you could probably look back on the video and see this time tag, and that could potentially be the problem. Yeah. So I think I just hit run system tests and I didn't hit submit. And it was running my old code, which was actually broken on this problem from, I think, like several years ago. I tried solving it maybe when I first started ICPC, and I didn't code this cleanly then. And the bug was I was only going in 4 directions instead of 8. So I submitted that code earlier just to see if it was working code, and it failed system test. So maybe I just didn't hit submit, which would be embarrassing. But yeah, I finished before the Topcoder educational round, which is useful. So hope you guys have fun competing in that. If you haven't already registered, register, have fun competing in the educational round. I think I'm going to look at the problems a bit later. Yeah, probably not going to compete. It's lunchtime here, so I think I'm going to grab some lunch. But I'll probably look at those problems later, and if something's really good to go over, maybe go over it next week. But I do have some ideas for things to go over next week I think would be a good episode. But I will see you guys all next week.